For nearly a century, the stretch of ocean between Miami, Bermuda, and San Juan has carried a reputation that outlived every attempt to explain it away. In 1945, 5 Navy training bombers lost their bearings over these waters during a routine flight and were never found, along with the rescue plane sent to search for them. In 1918, a 400-foot Navy cargo ship called the USS Cyclops left port here carrying more than 300 people and simply stopped existing. No wreckage, no distress call, no answer to this day. Stories like these built the legend, and by the 1970s, a best-selling book had given that legend a name, a map with 3 straight lines drawn across open water and a permanent place in popular imagination. And for just as long, researchers have pushed back against it patiently, insisting that nothing especially strange happens in these waters. Only weather, human error, heavy shipping traffic, and a name that became famous for reasons that have little to do with the ocean floor itself. By most statistical measures, insurers and the US Coast Guard have long found the area no more dangerous than any other heavily trafficked stretch of ocean, a fact that rarely makes it into the documentaries built around the legend. By the early 2020s, in the world of this story, most serious oceanographers considered the subject closed. The mystery belonged to documentaries and dinner table conversation, not to science. And then, a routine piece of commercial survey work returned a result nobody on the project was looking for. Stay with me, because once you understand what that result was, and why it took months before anyone outside the company believed it, the comfortable version of this story becomes much harder to hold on to. In our story, the company is called Meridian Subsea Mapping, a private firm contracted to survey a possible new fiber optic cable corridor across the Atlantic floor. Their work is not romantic. It is engineering. Before a single cable goes down, someone has to map the seabed in extraordinary detail. Every ridge, every slope, every loose patch of sediment that could shift and snap a multi-million-dollar line years later. The ships move slowly, dragging sonar arrays back and forth across grids that look, on a screen, like a farmer plowing a field underwater. Most of what comes back is exactly what you would expect. Flat plains of sediment, the occasional shipwreck, long-dead coral, the slow architecture of geology doing what geology does. Nobody expects mystery down there. The Bermuda Triangle, in this line of work, is just another patch of seabed with a famous name attached to it. This particular stretch had even been surveyed twice before, years earlier, by 2 unrelated companies working on different projects, and both had logged it as unremarkable. Flat sediment, gentle relief, nothing worth a second look. That history is part of what made the next part so difficult for the team to process. Because for several weeks, on a stretch of seafloor roughly 640 meters down, too deep for casual diving, too shallow to count among the Atlantic's true trenches, the sonar kept returning something that did not look like geology at all. To understand why that mattered, you have to understand what the team was actually looking at. Natural seafloor, even rocky seafloor, tends to be chaotic. Currents pull sediment into uneven sheets. Coral grows in clusters, not rows. Faults crack rock in directions dictated by pressure and time, not by any kind of plan. Even a shipwreck, over enough decades, breaks down into a scatter of debris that spreads further and further from the original hull, never holding a tight, repeating shape. When a sonar operator sees a perfectly straight line on a screen, the first instinct in every survey anywhere in the world is to assume it is a cable, a pipeline, or a wreck hull, because nature rarely draws straight lines at this scale. What Meridian's sonar was returning, in this basin, was not one straight line. It was dozens. Some ran parallel to each other with almost identical spacing. Others met at angles too clean to be the product of random fracture, buried under what later analysis would estimate as several meters of accumulated sediment. The shapes formed the rough outline of a low, sprawling formation, wide sections connected by narrower corridors, like the bones of something built rather than something broken. At first, the explanation seemed reasonable, and the Meridian engineers were not wrong to reach for it first. Submarine landslides happen constantly along basin edges like this one. When a section of an old carbonate platform, essentially ancient compacted reef and shell material, collapses under its own weight, it can fracture into surprisingly geometric blocks, especially where the original rock had natural bedding planes running through it. On paper, the theory held together well. Carbonate rock is brittle. It breaks along planes of weakness. Nature, after all, is fully capable of geometry on its own without any help. The Giant's Causeway on the coast of Northern Ireland is a famous real example. Tens of thousands of naturally formed basalt columns, many of them startlingly hexagonal, created entirely by volcanic rock cooling and contracting in a predictable pattern. No tools, no builders, just chemistry and time. If basalt could organize itself into columns that precise, there was no obvious reason a collapsed carbonate platform could not produce something that, to an untrained eye, looked engineered. Given enough time, a single collapse event could, in theory, produce rows of block-like rubble that look deliberate at a glance, but are underneath it simply the predictable behavior of stone breaking the way stone breaks. This was the explanation most of the senior geologists on the project wrote into their first report. It was not lazy. It was the version supported by decades of precedent in similar basins around the world. And for a while, it was the version everyone accepted. But that is where the story begins to crack. A junior data analyst on the project, a woman the story gives the name Elena Castell, had spent the better part of a year cross-referencing collapse formations from a dozen other surveys for an unrelated hazard mapping report. The unglamorous kind of work that involves looking at thousands of sonar images until the patterns of natural collapse become almost second nature. She knew in detail what a real submarine landslide looks like in sonar data, and what she was looking at here did not behave like one. Natural collapse rubble spreads outward in a rough fan, denser near the source and thinner as it scatters away, the way any pile of broken material settles under gravity. The formation in this basin did not fan outward. It held its shape. The spacing between the parallel lines did not loosen or tighten the way collapsed rock typically does. It stayed within a narrow, repeating interval again and again across more than 200 meters of seafloor. One detail refused to fit. Real collapsed rubble gets messier the longer you look at it. This formation was getting more consistent, and once you notice something like that, the old explanation becomes much harder to accept. Rather than raise an alarm, which is not something done lightly on a commercial survey project with deadlines and budgets, Castell asked for time to test the landslide theory properly. If the formation really was collapsed carbonate rock, she reasoned, a remotely operated vehicle equipped with cameras and a manipulator arm should be able to find the signature of a true fracture. Rough, irregular breaks, uneven surfaces, the visual chaos of stone giving way under stress. The ROV went down on a calm, overcast morning, lowered slowly through 600 meters of darkness until its lights finally found the bottom. What the camera sent back did not look like the chaos Castell had expected. The surfaces were worn, coated in centuries of fine sediment and the occasional patch of cold water coral. But where the silt had been disturbed by current, the underlying faces looked smoother than pure fracture tends to produce, block after block, the same flattened, almost deliberate surface. If this was a landslide, it was the strangest one anyone on the team had ever filmed. The result did not match the textbook. Before the case ever reached an AI system, the team tried something simpler and in its own way more revealing. Working from the ROV's photographs and laser scan profiles, a structural engineer under contract with Meridian set up a controlled comparison in a small materials lab outside Tampa. The goal was modest: take blocks of similar carbonate rock, simulate the kind of natural collapse the team still believed was the most likely explanation, and see how closely the resulting fracture pattern matched what the cameras had filmed. They dropped weighted carbonate slabs from measured heights onto a bed of packed sediment, again and again, logging the angle and spacing of every fracture. They also tried the opposite extreme. hand-shaping a smaller set of blocks using basic stone tools, the kind available to a coastal community working soft limestone thousands of years ago, to see how close human labor alone could come to the field's regularity. Neither test produced anything close. The dropped slabs fractured exactly the way real landslides do, in the chaotic, fanning pattern Castell had already flagged as missing from the actual site. The hand-shaped blocks came closer in form, but the spacing between them drifted by anywhere from 12 to nearly 30% from one block to the next, the ordinary variation of tired hands and shifting attention. Nothing in either test reproduced spacing this tight, this often, across this much ground. The lab notes from that week put it in one blunt line. The formation behaves like neither category we tested. That sentence, more than anything else, is what convinced the project lead to authorize a deeper analysis. This is the part of the story where the modern tool enters, and it is worth being precise about how it was used, because the team was careful not to let the technology simply tell them what they wanted to hear. Meridian had recently begun testing an AI pattern recognition system, originally built to flag pipeline hazards and unstable slopes from sonar and photogrammetry data. In plain terms, the system worked by converting every scan into a mesh of coordinates, then comparing the geometry of that mesh against a library of thousands of previously labeled formations, some natural, some man-made, some simply unexplained, looking for statistical resemblance rather than meaning. The team called it Argus, after the many-eyed figure from old mythology, mostly as an office joke about how tirelessly it scanned through terabytes of seabed imagery without ever needing a break. Argus had no archaeological training, no instructions about ancient civilizations, no concept of what a structure was supposed to look like. It was asked to do exactly what it always did: measure the geometry of the seafloor and flag anything statistically unusual compared to known natural and man-made formations in its reference library. The machine was not told what answer anyone wanted. It was only asked to measure what was there. What came back was the number that stopped them. Argus identified 211 distinct block-like formations within the surveyed area, with center-to-center spacing that varied by less than 4% across the entire field. A level of regularity its natural formation library had almost never produced from confirmed landslide or fault collapse data. Face angles across the blocks clustered tightly around 87 degrees, with most individual measurements falling within 2 degrees of that average. The system's own confidence scoring, built from comparing the formation against thousands of labeled natural and artificial structures, flagged the geometry as a natural collapse event with a probability of under 9%. None of this proved anything on its own. A statistic is not a conclusion, and the engineers reviewing the output knew that better than anyone. But a 9% probability of a natural cause is not nothing either. It is the kind of number that makes a serious team stop celebrating their first theory and start asking harder questions. Before reporting the result any further, the analysts ran a deliberate sanity check. They fed Argus a separate site from an entirely different survey, a formation everyone already agreed was ordinary collapsed geology, just to see whether the system would flag it as unusual too. It did not. The known natural site scored a normal collapse probability of roughly 78%, comfortably within the system's confident range, which told the team something important. Whatever was happening with the new formation, Argus was not simply flagging everything it saw as strange. What made the result harder to dismiss was something almost embarrassingly simple. A human surveyor, even a skilled one, drifts. Attention wavers. A hand angle shifts slightly with fatigue, with current, with the small unconscious corrections every person makes without noticing. The same reason no two signatures from the same person ever look perfectly identical. Even controlled experiments simulating ancient quarrying or hand-cut stonework tend to show measurable variation from one cut to the next. A few degrees here, a slightly different depth there. The fingerprint of a living person doing repetitive work. Natural geological processes are, if anything, even less consistent. shaped by pressure and chemistry and time in ways that rarely repeat with precision. What Argus had measured was neither. The spacing held. The angles held. Across more than 200 meters of seafloor, the pattern simply did not drift the way nature drifts, or the way human hands drift. A human hand drifts. A system repeats. The stone was not arguing. It was leaving a pattern. So the team did what any careful analyst would do next. They asked what the formation actually resembled, once natural collapse had slid to the bottom of the list. Argus compared the geometry against its full reference library: quarry walls, foundation terraces, breakwaters, reef structures, shipwrecked debris fields, collapsed mining tunnels, even modern offshore infrastructure, ranking each category by how closely its statistical signature matched the field data. The closest match was not what anyone expected, and it was not, despite what a few early internal messages reportedly joked, anything resembling a lost city. The single closest statistical match in the system's library was a class of low coastal terracing and retaining wall construction documented at several genuinely real submerged sites around the world, places where sea levels were dramatically lower thousands of years ago, leaving stone structures built on what was once dry coastline, now resting quietly underwater. The match was not exact. Argus scored it at roughly 61% similarity, far from certainty, and the system flagged the comparison itself as low confidence, given how few deep, heavily sedimented examples existed in its library to begin with. This did not prove that anyone had built something in what is now the open Atlantic. But it raised a question the landslide theory could not answer cleanly. Why would a natural collapse event resemble, more closely than any other category in the database, the specific geometry of deliberate low-wall construction? Here is where the story adds its hardest physical problem, the kind of detail that is easy to walk past and difficult to explain once you actually notice it. 640 meters down, in near total darkness, under crushing pressure, with currents strong enough to complicate even a modern ROV's stabilization, building anything resembling a deliberate wall structure would be, by any known historical seafaring technology, essentially impossible at that depth and in those conditions today. Even the ROV's pilot, an experienced operator who had logged hundreds of hours on far easier sites, described the current at the formation as some of the trickiest station keeping of his career, constantly nudging the thrusters just to hold a steady camera angle. Nobody on the team seriously proposed that ancient people swam down and built it underwater. The far more interesting possibility, meters lower than they are now, meaning large sections of today's submerged continental margins were once exposed coastline. If the formation in this basin predates that sea level rise, it would not need to have been built underwater at all. It would only need to have been built on land that has not been land for thousands of years, which raises a very different and much harder question about who might have been capable of building something like this, that long ago, on a coastline that no longer exists. None of this made anyone's job easier. Meridian was still under contract to deliver a viable, safe cable route, not to investigate an unexplained formation sitting in international waters, and more than one person on the project argued reasonably that the responsible move was to quietly reroute the cable around the anomaly, file a brief note in the final report, and move on. For a few weeks, that argument nearly won. What kept the investigation alive, according to Castell's later account, was less a sense of discovery and more a kind of professional discomfort. The feeling that a result this unusual, sitting unexplained in a company's own data, was the kind of thing that comes back to embarrass you later if you simply ignore it now. The deeper evidence is where the case stopped being only visual. A short sediment core, recovered beside one of the larger blocks, gave the team something sonar alone never could: a physical timeline. Layer by layer, the core showed centuries of fine accumulated silt resting directly against the block's surface, undisturbed, the way sediment settles only over very long, very stable periods of time. A second sample, a small fragment chipped from the block itself, went to an outside lab for mineral analysis. The composition came back as fairly ordinary marine limestone, nothing exotic, nothing that pointed toward any single source location, which on its own settled nothing either way. Ordinary stone can be natural or it can be quarried, and the chemistry alone could not tell the difference. What it could rule out was contamination from anything modern. No trace of cement, no metal residue, no chemical signature consistent with anything built in the last few centuries. Under magnification, the exposed stone face showed something the geologist had not expected to find. Faint, closely spaced parallel striations running in the same direction across multiple separate block faces, the kind of fine surface marking more often associated with repeated directional working of a stone surface than with the random scarring of fracture or current erosion. The team was careful here, and so should we be. Striations like this can occur naturally through sustained current action over very long timescales. But the consistency of direction across physically separate blocks was, in Castell's own notes, the part most people would walk past without noticing, and the part she could not stop looking at. And that is where the timeline begins to bend. Sediment accumulation rates for this region, based on comparable cores from nearby surveys, suggested the layer directly covering the formation had been building for somewhere between 9 and 12,000 years. A window that lines up unsettlingly well with the period when this part of the Atlantic margin would have sat closer to the surface, possibly even partially exposed, before the post-glacial sea level rise reshaped the coastline entirely. For comparison, the oldest confirmed monumental stone construction known anywhere in the real world, a site called Göbekli Tepe in modern-day Turkey, dates to roughly 11 to 12,000 years ago. And its discovery alone forced historians to push back their estimate of when organized building first began by several thousand years. If the dating on this fictional formation held, it would sit in that same narrow window, or possibly earlier, on a coastline that, unlike Göbekli Tepe's, no longer exists at all. That is not a small claim, and nobody on the team treated it as a settled fact. But it is the kind of number that, once it is on the table, is difficult to simply forget. Either the dating was wrong, the geology was being misread, or something was built on this stretch of coastline far earlier than the official timeline currently allows for. One example, on its own, could easily be dismissed as an unusual but ultimately natural formation. A strange-looking accident of geology that simply has not been fully catalogued yet. That is, in fact, the most likely outcome, and it is worth saying plainly even inside a story. But in this story, it did not stay one example. Word of the Argus analysis reached two independent research groups working on unrelated submerged landscape projects. One studying drowned coastal terrain off a different continent entirely, the other reviewing decades-old sonar archives that had never been reanalyzed with modern pattern recognition tools. Both groups, working separately, without coordinating with Meridian, reported formations with a similar statistical signature. Tight angular clustering, repeating spacing intervals, sediment burial consistent with great age. One of the two sites sat at a comparable depth in a different ocean basin entirely, with a spacing variation Argus measured at under 6%. Close enough to the original field's 4% that the analysts flagged it for direct comparison rather than treating it as a separate case. None of the three sites resembled each other in overall shape. One was long and narrow, another roughly circular. The third irregular and broken by what looked like a more recent fault line cutting through it. But the underlying numbers, the regularity, the consistency, the way the spacing refused to drift, rhymed in a way that was difficult to dismiss as coincidence. One site could be a mistake, but the same signature appearing somewhere else changes the question. So where does that leave the story we started with? A comfortable, decades-old explanation for a stretch of ocean that everyone agreed had already given up its secrets. It leaves it with a harder question, sitting underneath the easy one. Is the official geological explanation simply incomplete, missing a category of natural formation that produces this kind of regularity and has not been properly documented yet? Is the dating on the sediment cores wrong, placing something recent into a timeline that makes it look impossibly old? Or is it possible that what we think we know about early coastal habitation, who was capable of organized construction and how long ago, is less complete than the textbooks suggest? None of those three possibilities is comfortable in quite the same way the original case-closed version of this story was. The mystery in this story did not get smaller the more it was examined. It got wider. There is no tidy answer at the end of this one, and that is true even inside a story built for the screen. Maybe what Meridian's sonar found really was a freak, beautiful accident of geology. A collapse event so unusual that it simply has not been matched in any database yet. Natural and explainable once the right comparison finally turns up. Maybe the sediment dating is off by thousands of years, and the formation is far younger and far less mysterious than the numbers in this story suggest. Maybe it points to something genuinely uncomfortable, a method of construction, or a period of human capability that does not fit cleanly into what we currently believe about the deep past. Or maybe, as is so often true with stories like this one, the real answer is something we do not yet have a name for, sitting quietly in the dark, waiting for the right tool or the right question to finally bring it into focus. Before you go, one more reminder because it matters. Nothing in this video describes a confirmed real-world discovery. Meridian subsea mapping, Argus, and the formation beneath the Bermuda Triangle are fictional, invented for this story alone. The real history behind the legend, the real ships, the real statistics, the decades of real investigation into these waters is its own subject, and a genuinely fascinating one if mysteries like this are what keep you watching. So tell me in the comments, if a story like this one turned out to be true, which explanation would you believe? The natural accident, the dating error, or the uncomfortable possibility that the timeline is wrong? I read the comments, and the most interesting theories almost always come from you. And if stories like this are the ones that keep you curious, subscribe and stay close, because the next mystery is already waiting to be